Hi there. So I just want to quickly go over the characteristics of proton NMR spectrum and what you need to know in order to read NMR. So the first is going to be the number of signals. The second is going to be the signal location. The third is going to be the signal area or the integration. And the last is going to be the signal shape or the splitting pattern. So when we talk about the number of signals, protons with different electronic environments will give you different signals. For example, if we were to look at this structure right here, imagine that instead of just a carbon, this is a CH3. If there happened to be another CH3 on the other side, and that was the full molecule, it wouldn't show up on the NMR as two different carbons, if that makes sense. It would just show up as one because there's no real difference in between what they look like and their genetic and their environment. So there wouldn't really be too much difference there. There are two types of atoms that really look like that. So there's homotopic, which are just straight up atoms that are equivalent. And then there's protons that are disastrotopic, which are not equivalent, but then there's also protons that are enantiotopic, which are equivalent. So protons are homotopic if a molecule has an axis of rotational symmetry that allows one proton to be rotated onto another without changing the integrity of the molecule. So again, if you look at this and imagine there was a CH3 right here and a CH3 right here, then if you were to flip that molecule and the CH3 actually moved over here and this CH3 moved over here, again, there would be no difference, which is why there's not a real difference in those two molecules. So now we're going to move on to signal location. Signal location refers to where a particular proton absorbs depending on its electronic environment. So we have the most important part of figuring out where it's going to absorb is based on its shielding effects. So shielding effects means an electron shields the nucleus and the absorption creates a magnetic field. So when it shifts upfield, which it sounds confusing, but it's actually going to be towards this way, it's going to have a larger induced magnetic field. So the more shielded a proton is, they don't have as many magnetic forces that need to act on them. So they have smaller energy gaps and absorb lower energy radio waves, which is kind of the basis for NMR to absorb those waves. So because of that, it's going to be found mostly on these sides. So like alkanes, alleles, ketones, aldehydes, all of these guys are going to be more upfield. Downfield is going to be when there's a decrease in electronic density, and so it de-shields a nucleus, meaning the absorption shifts downfield. So they're not as shielded, and because of that, they have to produce more energy because they're getting in contact with those radio waves a lot more often. So ones like ketones, aldehydes, carboxylic acids, those ones are going to be considered more downfield because they absorb the energy, they absorb the radio waves a lot more than alkanes, alleles, and all the guys that are on this side. So now we're going to go into, sorry, I'm pulling it up, the integration, which is the intensity of signals. So we have the integration, which is the area under the peak, quantifies the relative number of protons giving rise to a signal. A computer will calculate the area of each peak representing that curve with the step curve, which kind of looks like a little S. And a curve height represents the integration. So it's overall kind of like how many protons are in a signal will show how tall it is. So the taller a peak is, the more protons that are neighboring that proton. So To determine the number of protons that will give rise to an NMR signal, you divide the total number of integration units, which will be given to you, and then you divide that by the total number of protons. So the next one that we're going to go into is theory of spin-spin split. So splitting signals into multiplex is called spin-spin splitting, which results when two different types of protons are close enough that their magnetic fields influence each other. Equivalent protons don't split each other. Again, they don't really show up too much on the NMR. And splitting is only for non-equivalent protons on the same carbon / adjacent carbons. So if you were to have one carbon and it has 3 carbons on it, then it would, or even better, if you had one CH3 and it was attached to one CH3 and another one CH2 and another CH2, then it would split a signal because it's splitting it between those two. But then since they're both CH2s, there's still only one carbon on there. So it would be 2 signals and they would each split into 2 because it's the doublet of doublet rule. So now that we've gone over that, we're gonna look at a few NMR spectras and we're gonna see how well we can explain them. So the first one I wanted to go over, this is ethanol. So in ethanol, it looks like it would just have a lot of signals because you have H, 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 but remember we're only looking at the carbon 13 NMR. So this is actually the solvent, and we know this because it's at 0. There's no actual, if you look at it, there's no actual bond that goes to 0, except for carbon and iodide, but there's no carbon and iodide in here. So we're just gonna ignore this and say that it's like solvent or just something around that. And we're gonna look at these two. So this one is carbon 2 and this one is carbon 1. So you might be a little bit confused as to the number difference. This is gonna be based off of the integration, and this is also based off of the shift. So the CH2 is actually not going to be as upfield or not going to be as downfield. It's going to be more upfield. And this is because it's surrounded mostly by hydrogens. So there's a good amount of shielding happening. There's no vast electronegativity difference that's going to affect shielding in any way. So it's going to be a little bit more over this way. And then over here, we have carbon 1, which as you see is attached to an oxygen, and that is greatly going to affect it because since there's more electronegativity, it does pull away electrons, which affects shielding, and because of that, it does have less shielding happening for that carbon, and as a result, it's going to be a little bit higher up here. So there's not too much to say about this, honestly. This one's a little bit higher, as you can see, but that's mostly just because it has more atoms surrounding it versus this one only has like 3. This one has about 4, even though this one's not necessarily connected to it. It is there and it's surrounding it a little bit more. So that's why this one is a little bit taller, then this one is a little bit more downfield just because it has something so electronegative next to it. So now we're going to move on to ibuprofen. Ibuprofen is a little bit of a tricky one because there's so many, there's so many signals that attach to it, but it's easy when you start breaking it down a little bit more. So this right here, we can see is a carboxylic acid. And then it also just has a lot of CH3. So we have a CH3 here, we have a CH3 here, a CH3 here. We have an aromatic structure, which we need to look for. we have a CH2 and we have a CH2 right here. So right off the bat, we can see the carboxylic acid. We know that it's something that has to do with this oxygen over here and with this alcohol right here, because it's so downfield. And so we know that it's this guy right here, and we can pull it up on our spectral data. So if you look right around the 180 mark, that's going to be a carboxylic acid, an ester, or an amide. Luckily, we don't have a nitrogen in there, so we know that it's not an amide, and we know it's not an ester because there's no it's like OR. It's not it's OH, and esters are more OR. So this one would be like O, and then it would be like a CH3 or something. So we know for sure that this is a carboxylic acid, and this carbon is really signifying that. So that's likely coming from this guy. This right here looks confusing and definitely confused me on the exam a lot because they're so close to each other. So you know that they have an effect on each other and that they're likely neighbors, but then one of them's like really big and two of them are really small. So these actually just signify aromaticity. So if we want to look on the structure for aromaticity, we will look towards the middle, that benzene. That's really signifying these guys right here. So if we look on the NMR spectrum, because this is about 120, it's probably a little more than 125, but we'll say about 125, and then this one's almost exactly 140. So if we were to look at that over here, it starts around 115, I would say, but it's between 120 and 160. I feel like it would be, you would know if it was an alkene, because there wouldn't be like this oddness in like too big, too little. And like if it was just a normal like straight chain alkene, it would just be like that. However, since there's a bunch of alkenes in the aromatic structure, those are mostly going to show up. Let's see. So it's a little bit further back than aromatic structure. So it's likely going to be the two big ones, and then the two small ones are just also displaying that aromaticity. So now we have these guys right here. So we have about 45 marks. So we'll go over and we'll look around 45, which will probably be around here. So we got a carbon and a chlorine, a carbon and a bromine, carbon and a nitrogen. We have a ketone. So I believe that one would also be just signaling this guy right here. We have one at the 30 mark. So we don't have a carbon iodide. Like, I'm listing all the ones that it could be, but we know that it's not any of these guys, only because we don't have those atoms in the structure. So we have the carboxylic acid and the amine. So this structure right here, it could, I keep opening the wrong one. It could signify to like this guy right here, where it's, so it could be a signal from one of these two that's showing like this carbon is attached to this carbon, which is attached to this double bond. We have one around the 20 mark. So I'm gonna say the only real one I see over here is that carbon on carbon. And it's definitely not going to be this one, but just because, again, we already pointed out that it's going to be a little bit more downfield because it's attached to a carbon that is being super deshielded. So because it still is a carbon on carbon stretch, it's likely going to be either this one or it's going to be one of these. I believe that it's likely going to be this one, just because it still is a little more downfield than whatever one this is. So now we have about 19, which is still around that 20 mark. So like I said, these two are going to count, aren't really going to count because they are equivalent, but we do have that connection to this guy. So I'm going to say that this one right here is this one right here. And it's really, sometimes it feels really difficult to read NMR. However, if you ever do struggle, there's also plenty of other avenues you can look at. For example, I'm looking at the spectral data just for carbon NMR. However, if you scroll up, there's one for hydrogen NMR. There's information about the IR spectra. There's another one. There it is. This one's just the wave number and the functional group region. So once you put all of those together, it is a little bit easier to understand it. Like for example, on the exam, we actually had to guess the structure. And so we couldn't just be like, oh yeah, this one's probably this one's probably this one's blah, 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 blah. We actually had to come up with it, which was definitely a lot easier when we had IR, NMR, CNMR, and HNMR. So that's all I have for today. I hope you guys have a great rest of your day, and I'll see you soon.